Hey guys, and welcome back to another video. It's been quite a while since I've made one, but I'm making one now because I want to make educational videos, and I know I've talked about this in the past, but I think I'm actually going to do it. And so my reasoning behind doing this is because I want to pursue kind of like a faster education than like the schools in my area allow. So I teach myself outside. But I've read a bunch of papers and studies talking about how actually like the best way to learn is to teach something you've recently learned, and that reinforces it in your brain. And so I've recently learned Calc A through C. So I'm going to be doing a video series on that. And so I'm going to kind of skip over limits because I'll kind of incorporate them as I describe derivatives, integrals, and series. And so I'll kind of go as it is. Okay. And I mean, if you want to learn limits, go to Khan Academy. It has an excellent thing. They have an excellent Khan Academy has an excellent way for learning basically everything. But if you want another perspective, or maybe a different person teaching, I don't know why, because you got Sal with that classic voice there. So, all right. So today's video will just be kind of focusing on what is a derivative. I won't be going into like the rules and stuff, but I will be explaining what it is conceptually. Alright. So, imagine that I can draw well with a mouse, which I can't, but imagine, like, this would be straight, these are straight, and this is a better bell curve than it is right now. So, right here, with traditional algebra, you know how to do the slope. It's delta y over delta, oh, that's a derivative sign. Let's get rid of that, over delta x. And so we would know that if this is point y1 and this is point or x1 y1, then this would be x naught y naught, and that's what you call when it's a subscript of 0. It's naught. So x naught y naught, and then you would subtract these and take these from these values in with this, and that's really all that delta y means. It's just the y1 minus y naught over x1 minus x naught. And so with this kind of like a thing, we know that it's the change in the height along with the change in the x direction. Let me go and change up these colors a teeny bit. Alright, and so we can kind of get the rate at which function's value changes. And so if this white thing over here is a graph of f of x, and I do apologize, I write my f's of x with the cursive f. I don't know why. I think it's because my capital F's and lowercase f's, like if I draw like an f like this, it's pretty much the same as how I draw other f's, so I draw a cursive one. So if this white thing over here is the f of x, well, it's just a line, and so it's going to have a constant slope, and which would be m, and you know, mx plus b, where b is the I believe y-intercept. So, oh no, it is the y-intercept. I don't know why I said believe there. Okay. So we know that this would be the slope here would be equal to this thing, and we can all agree that it wouldn't change as you change this value, or as you change x. Y, the rate of change of y is not going to change at all because it's a constant thing. And as you get more into derivatives, you know, as you take if you took a derivative of a linear function such as this one. If you're taking it with respect to x, it would turn into just m, and so that's how you could kind of prove that. But we're going to kind of get into this. So if I was going to zoom in to a part of this function, and let's call this g of x. So if we zoomed into it, so it would be green. Here, let me kind of go down here. It would be green, and it goes down like this, as you can kind of imagine that. And you can kind of see like right here, but like even if we got it a little closer, go back to my green. If we got a little closer, you could see that it starts to kind of look like little segments of lines, you know, like infinitely small segments of lines, and that's kind of what limits are. So to kind of, I'm going to kind of go over just a basis of limits. I recommend you go see Khan Academy's videos on limits. But say you have a limit as x, which is just any value of the value of the function, as it approaches some number, which we're going to choose infinity. The value of x as it approaches infinity, right here. But like if we're going to have the slope right here, like so it would be this. It'd be like the value of the slope, which is going to be delta y over delta x. And so the thing with that's interesting here is because you would see if you did delta x, if you used this equation, which is good for linear functions and trying to determine the slope of a linear function. If you're trying to determine the slope of a curve like this, you would kind of get you just get a line, and that's called a secant line. And it's kind of like it's an approximation, but it's not accurate. And so if you wanted to get more and more accurate, you'd want to create lines that were closer and closer and closer and closer and closer until they were infinitely close together. And so this is kind of like the idea of a derivative. And so if you wanted to find the instantaneous rate of change of something, then you take the derivative, because it's like finding the slope at that exact point. Because as we could probably all agree, a parabola doesn't have a constant slope. And I bet you $500 that a parabola doesn't have a changing slope. If you wanna take me on that bet, then I am willing to accept $500 from you. But yes. So, taking that into account, that's kind of what a derivative is, and so we'll kind of talk a little bit more about how, here I'm going to go and erase some of this, some of the like bare bones principles of how to kind of use a derivative in context, like how to kind of think of something. Alright, so we'll think of a parabola. Oh, that's think of a parabola, and if this is my if this is like position, so as I change, let's say we'll use t, which is t is equal to time, and then it changes, let's say, my y position, so my change like in height over change in time. And so the way this would work, we can see that as time increases at one point, it's lower, and then it's higher and higher and higher, and then it's lower and lower and lower. And so you could come up with some function that you could come up with a function describing the way y is to t, and let's just say we're going to, I know that this won't match correctly to it, but we'll say, let's say f of t is going to be equal to, and then we'll just say something like t squared plus 1. Make it interesting, but not too interesting, because this is just an introductory video. Alright, so it would just be this f of t right here. Basically, this symbolizes like the y, the value y. And if you don't know that by now, then I recommend you not start learning calculus right now. Alright. So if we take a derivative, and I'm going to take the derivative without explaining any of the rules here, just so you can kind of get an idea. So a derivative, if I took the derivative, which you can mark using a prime right here of t, so you would say f prime of t, which is the first derivative, that would be 2t plus 0, because I'll talk about it later, but the derivative of a constant is a 0. So this becomes 0. And because you'll notice that this actually becomes a linear function. It is no longer a quadratic function. It is now a linear function. And so you'll notice that if you have a function that has a power to it, then as the derivative increases, and say like we take the second derivative, t is equal to, so that would just turn into a 2 plus still a 0. And I'll explain these rules in greater depth in another video, but right here, so if we created like a graph of this one, so of f of t, right here, it's just a parabola. If we create a graph of this one, it's just a line. And then if we created a graph of this, it's a horizontal line with no change in slope, or no change in the y value. And so if you were to think about this, this is your change in position. This is going to be your rate of change of position, so it would be your velocity. And this would be your acceleration. And kind of an interesting way to think about this is, if position is going to be in meters, then when you go to velocity, it goes to meters per second. And then when you go to acceleration, it's meters per second squared. So as you take a derivative, it's the rate of change of something per that unit of time, and you just increase, you divide it by, again, another unit of time, because you can rewrite this thing. It is equivalent to m over, here, let me move down, m over s, and that is equal to m over, s squared. And so that's kind of what the idea of a derivative is. It's not super complicated. If you have any questions, you can ask in the comments. I will answer it. If you really think I'm just a sucky teacher, then I guess I don't blame you. So go to Khan Academy then. Again, I'm trying to teach this so I can reinforce the ideas in my mind, but if it helps other people out at the same time, then, that's good. So in the next video, I will go over more in depth into the rules. I will cover the product rule and some of the other natural things of a derivative and how you can apply it. So yeah, check back in the next one.